So, hello, welcome to NPTEL Algebra 1 course. So, I am one of the PMRFTAs for this course. I'm Shubhojit, and welcome to week 6. So, this week you have studied about rings and other kind of, special types of rings, integral domains, Euclidean domains, principal ideal domains, and all that. And as we do every week, we'll be solving some problems based on that. So I hope you have attended Harish's TA session, and he solved some problems from the previous year assignment. I'll be solving the rest. So let's start. So let us start with the first problem, and the first problem is it's simple. It's nothing difficult. So you know that Z9 is a ring, right? Under the usual addition modulo 9 and the usual multiplication modulo 9, it forms a ring. And you know what units in a ring are, right? So basically, if R is a ring and U is an element of R, U is called a unit if precisely if U is invertible under multiplication, right? So U is a unit if there exists a V in R, right? Such that UV equal to VU equal to 1, right? Where 1 is a identity element under multiplication of the ring, right? So this is precisely what a unit is in a ring. So the first problem is basically asking us to find out what are the non-units in Z9. So what are precisely those elements in Z9 which are not invertible under multiplication. So this is something that I hope you already know this, that in Zn under addition modulo n and multiplication modulo n, an element A is a unit, that is it has an inverse under multiplication if and only if GCD of A comma n is equal to 1. So what I basically mean here is an element class of A, right? Every element is an equivalence class or a congruence class, and it is a unit if and only if the GCD of A comma n is equal to 1. This you can check very easily. I hope you have already done this previously, but you can again check it very easily. It's very simple. So now out of all these options, we see that the GCD of 1 comma n is 1. Here for our problem, n is given to be 9. Okay, now GCD of 1 comma 9 is certainly 1. GCD of 2 comma 9 is again 1, right? GCD of 4 comma 9 is also 1, but GCD of 3 comma 9 is 3, right, which is different from 1, right? And hence we can therefore say easily that hence 3 is the correct option. Not 3, 3 is the correct answer, I should say. Yeah. Hi Shalini, can you hear me and see my screen? Can you just...
Yes, sir.
Okay, thank you. So I was just talking about the first problem. I hope it's very simple. I hope you are completely okay with this. You just need to find out the non-units in the ring Z9, right? And you understand that an element in the ring Zn is is a unit precisely when a GCD of the representative of that element, of a representative of that element with n is 1, right? So a class A is a unit in Zn if and only if the GCD of a comma n is 1, right? This you know, right?
Yes, sir.
Yeah, precisely precisely the group of units of Zn is just Zn cross or Un, which you popularly know. So yeah, 3 is the correct answer here because only the GCD of 3 with 9 is different from 1. Okay, so let's move to the second problem. Now this problem you have studied about ideals this particular week, right? And this problem is basically asking you to identify the ideals of Z cross Z. Which of these four options are basically ideals in Z cross Z? So we can do this by explicitly checking one by one, but there is something more powerful going on here. I mean, for the case of rings, this is very powerful. So just recall that if G and H are groups, then G cross H, that is the direct product, is a group, right? You have studied this. Now if I ask you to find out a subgroup of G cross H, can you give, I mean, I don't want an example. My point is, you understand that if A is a subgroup of G and B is a subgroup of H, then certainly A cross B is a subgroup of G cross H, right?
Yes, sir.
But is a converse true? That is what I want to say is, if you take any subgroup of G cross H, is it always of the form A cross B, where A is a subgroup of G and B is a subgroup of H? Is that true? If it isn't, can you give me an example, counter example to this? So you understand the question, right? You take a subgroup of G cross H. I am asking you whether you can find subgroups A of G and B of H such that A cross B is this particular subgroup that you have chosen. Whether every subgroup can be written as a product of two subgroups. Is it true or is it false? What do you think? So I just want an answer. Is it true or is it false? It is false, right? Because you can just take Z2 cross Z2, right? And you understand very well that 0 0 and 1 1, these two collected in a set, this gives you a subgroup of Z2 cross Z2, right? It's closed under the operation as well as taking inverses, right? Isn't it?
Yes, sir.
Yeah, but certainly it is not of the form A cross B, where A is a subgroup of Z2 and B is a subgroup of Z2, right? That's also very clear, right? Because if it were of this form, then both 0 and 1 should be in A and both 0 and 1 should be in B, right? But then 0 comma 1 should be in A cross B and 1 comma 0 should be in A cross B. But this subgroup doesn't contain any of them, right? So the point is, it's not true that every subgroup is a direct product of two subgroups. But the situation changes drastically when you have rings or when you are working with rings. So what are the right analogs for normal subgroups in the case of rings?
Ideals.
Yes, ideals. So you can check this, that So I'll just give you a small hint to this, but it's very easy. But check that if let's say R and S are two rings. By ring I always mean a ring with one. Okay, it need not be commutative, but it's always a unital ring. Associativity is one of the axioms. We always assume there is a one. So if R and S are two rings, then R cross S is a ring, right? There's no doubt about that. The operations are basically component wise. Addition and multiplication are component wise. Now the point is this, that every ideal of R cross S is of the form I cross J, where I is an ideal of R and J is an ideal of S. So this is really true in the case of rings. It wasn't true in the case of groups, but it certainly holds in the case of rings. And the idea behind this is simple. So the point is that J is an ideal of S. So this is just a hint to this. You can check it very easily. So take any ideal. So take any ideal, let's say ij, what other letters are there? Take any ideal k, let's say, of R cross S. Okay. Consider the projections. You know that there are projections from the product onto the various factors, right? So let's say pi 1 R cross S to R say pi 1 is from R cross S to R. So what is this projection map, by the way? So it just takes little a comma little b onto A, right? And we have one other mapping pi 2 of R cross S into S, which takes A comma B onto B, right? These are the canonical projections. They are ring homomorphisms clearly. And what you do here is you just consider these projections and consider the images. So K is a subset of R cross S. It's an ideal of R cross S. And what you do is you consider the image of K under pi 1 and pi 2. So this is so consider, consider the ideals, I should say. You can check this, that pi 1 of K. So consider the ideal pi 1 of K of R and pi 2 K of S. Okay, these are ideals in R and S. It's not in general true that if you take an ideal, let's say you have a mapping of a ring R into a ring S, a ring homomorphism, and you take an ideal in R, its image need not be an ideal in S, but the image is always an ideal in the image subring, right? The image of R. That is what I'm saying. Now pi 1 and pi 2 are surjective ring homomorphisms, right? They are precisely epimorphisms, and hence they will always map ideals onto ideals. So pi 1 of K is an ideal of R, pi 2 of K is an ideal of S. So consider these two ideals and try to show that the original ideal K that we started with is equal to pi 1 of K cross pi 2 of K. So is it clear what I am trying to say? Are there any questions? Is it okay?
Yes, sir.
Yeah. So the point is that if you take a product of two rings, then every ideal in the product is precisely a product of two ideals. That is what is going on. And from this we can easily solve this problem. Of course, we could do it just by directly checking the all the properties of an ideal, which of these sets satisfy the properties of an ideal, but this is another approach. Okay. Now clearly you observe that A cannot be written as a product of two subsets of Z, and B similarly cannot be written as a product of two subsets of Z. Simply because of what of what we had in the case of groups, in the case of the claim for group Z2 cross Z2, just what we considered previously, right? So basically, let me just give you a small argument if it's not clear. So let's say you take this set A comma A where A is in Z. Assume that it is of the form A cross B, let's say. Then certainly this means that every A in Z is in A, right? That is, A has to be Z and B has to be Z, right? Which means in particular, for example, say 1 2 also belongs to this, but 1 2 clearly doesn't belong to this, isn't it? So it cannot be written as a product. So option A is wrong. It can't be written as a product of two ideals, let alone it can't be written as a product of two sets only, let alone two ideals. And similarly, B also can't be written like that for the same reason. But option C is correct. Sorry, option C is correct and option D are correct. D is correct. Why is C correct? So option C. So you have 2A comma 0, right? Such that A is an integer, right? And this clearly, as you understand, is 2Z cross 0, right? 2Z is an ideal in Z and similarly 0 is an ideal in Z. So certainly this fits, right? This is an ideal of Z cross Z, right? Right? And option D is also correct. So you have 2A comma 2B. So note that the coordinates are independent of each other, where A and B are in Z, and this is precisely 2Z cross 2Z, right? This is also an ideal of Z cross Z, right? Is it okay? Do you have any questions? So option C and D are correct. Is it okay? Someone can reply in the chat if someone has a problem.
Yes, sir.
Okay. Okay. So let's move on to the next problem. Yeah. So the next problem is again a question about ideals, and to be more precise, it is about a question about operations on ideals. So given two ideals, we have some operations to combine them and obtain a third ideal. That is what this third problem is all about. So you are taking a commutative ring R and you are taking ideals J1 and J2 in R. Then you are asked to find out which of these are ideals, A, B, C and D. So let me ask you this one. Is A an ideal? Is option A, that is the union of J1 and J2, is this an ideal of
No,
okay.
sir.
Okay, can you give me an example?
Sir, in Z, ideal generated by 2 and
Yes.
ideal generated by 3. Both
Yes.
are the ideals, but their union is not an ideal.
Okay, yes. Their union is certainly not an ideal, right? Yeah. So, and why is a union not an ideal? Because, for example, 2 is in one and 3 is in another. So 2 and 3 are also in the union, but clearly 5 isn't, right? That is what you want to say.
Yes, sir.
Yes. So you can check this, that J1 union J2 is an ideal if and only if J1 is contained in J2 or J2 is contained in J1, right? In fact, you don't need to even go to ideals. This is true for subgroups. You take two subgroups of a group, you take their union. That union is a subgroup if and only if one is contained in the other. Okay, so clearly J1 union J2 is not an ideal in general. So we can discard this option. Now let's see option B. Is J1 intersection J2 an ideal?
Yes, sir.
It will be, right? So a small, let's just check it quickly. So assume X and Y are in J1 intersection J2. This implies that x plus y is in G1 intersection J2, or rather let's say x minus y is in G1 intersection J2, right? So it's closed under subtraction, and if R is in your ring R and x is in G1 intersection J2, this will imply that Rx is in G1 intersection J2, right? Precisely because G1 and J2 are ideals. And certainly 0 is also in G1 intersection J2, which shows that G1 intersection J2 is an ideal. Yeah. So let's now look at option C. So is G1 plus J2 an ideal?
Yes, sir.
Okay, good. So G1 plus J2 is also an ideal. And I mean the reason is again the same. So let's not go into checking all this, but yeah, you can do this very simply. It's very simple. What I want to say here is you can check something extra. Check that G1 plus J2 is precisely the ideal generated by G1 and J2. Do you understand what is the ideal generated by, let's say, a subset or two sets or whatever, a subset of your ring? So instead of writing G1 and J2, we can also write G1 union J2. So do you understand what is the ideal generated by G1 union J2? I mean, suppose you take a ring and you take a subset of that ring. Do you understand what is the ideal generated by that subset in the ring? You certainly studied this for groups, right? That you take a group, you take a subset, you consider the subgroup generated by that subset, right?
Yes, sir.
So what can be the, yeah, sorry. So what can be the appropriate or appropriate analog in the case of rings? What is the right analog in the case of rings? So you take a ring R, you take a subset S of R. What is the ideal generated by S in R?
It is of the form RS, where R belongs to R and S belongs to S.
That's a bit wrong. I mean, this will not be an ideal, right? Because if you take R1 S1 and you take R2 S2, there's no guarantee that the sum is also in this, right? So what you want to say is it should be of this form. Every element should be of this form. RK, SK, let's say. This is what you want to say, right? Every element should be a finite sum like this. Then it's an ideal.
Yes, sir.
Yeah. So I didn't want an internal description of this, but can you define it externally, just as you did in the case of groups? Yeah, by the way, by a ring here, I am talking about a commutative ring with one as given in the problem. Okay. Of course, you can make sense, you can define the appropriate notions in the case of non-commutative rings or rings without one, but then describing the elements in the corresponding generated ideal would be a bit difficult. Okay. That would be a bit difficult, but we just focus on commutative rings for the time being. So what do you think is the ideal generated by S? I mean, can you give me an external definition or description? So you have studied this, right? That the ideal the subgroup generated by a subset of the group is precisely the intersection of all subgroups containing that subset, right?
Yes, sir.
So we can make the appropriate similar definition here as well. So the ideal generated by S will be the intersection of all ideals of the ring containing the subset S. Or in other words, it is the smallest ideal of the ring containing the subset S, and that's it. From this you can easily figure out what are the elements in the ideal. As you said, the element should be of the form R1 S1 plus up R2 S2 plus dot 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 up to Rn Sn. Finite sums of those forms. So this is precisely the definition, and you can check that G1 plus J2 is precisely the ideal generated by G1 and J2 or G1 union J2, whatever. That is, G1 plus J2 is the smallest ideal of your ring containing both G1 and J2. And that's very easy to see. Because I mean, we can in fact give a proof here only J1 is contained in the ideal generated by J1 union J2. J2 is contained in the ideal generated by J1 union J2. And since ideal generated by J1 union J2 is an ideal, so the sum J1 plus J2 should also be contained in this ideal, right? And what is the converse direction? So J1 is contained in J1 plus J2, right? We understand what J1 plus J2 is, by the way. It's our element, it is the ideal of all elements of the form x plus y, where x is in J1 and y is in J2, right? That you understood. So which is why I didn't bother to write the description. So anyway, so J1 is contained in J1 plus J2 and J2 is also contained in J1 plus J2, which means that J1 union J2 is contained in J1 plus J2, right? Now J1 plus J2 is an ideal, and what do we know about the ideal generated by J1 union J2? This is the smallest ideal containing the set J1 union J2, right? But we already saw that there is some ideal containing J1 union J2, right? And this has to be the smallest one, which means that this has to be contained in J1 plus J2. So my point is that these two are the same. The ideal generated by J1 union J2 and the sum of the two ideals J1 plus J2 is the same thing. So option C is certainly correct, right? And what about option D? By the way, by J1 J2 I mean this: all elements of the form summation xi yi, I running from 1 to n, where xi is in J1, yi is in J2, and n is any integer. I mean n is a natural number. So J1 into J2. This is what the product of two ideals is precisely has this definition. Okay. So what do you think? Will this be an ideal or not?
Yes, sir, it will be an ideal.
It will be an ideal, right? Again, you can check it very easily, and just using the you can clearly see, in fact, that the sum of elements, if you take one element which is a finite sum like this and another element which is a finite sum like this, you add them up, that will clearly be a finite sum like this, right? So it will be in J1 J2. And similarly, if you just take any element which is a finite sum like this and you take a ring element, multiply it with this, you again get a finite sum, precisely because multiplication distributes over addition, right? So J1 J2 is clearly an ideal. So what I would ask you to check here is, check that J1 J2 is equal to the ideal generated by, what do you think? What should be a generating set here? This is also generated by some subset, but what subset should it be? J1 and J2 are ideals.
Intersection?
The intersection won't work, right? Because suppose you take the intersection, this is already an ideal, right? So if you consider the ideal generated by this, what do you get? What is the ideal generated by a subset? It's the smallest ideal containing that subset. Now J1 intersection J2 itself is an ideal. So what happens if you take the ideal generated by this? That is what happens if you take the ideal generated, I mean the smallest ideal containing J1 intersection J2. That is precisely J1 intersection J2, right?
Yes, sir.
Yeah, so J1 intersection J2 won't work, but there is some different set that you can take here. So you can check that this is precisely the ideal generated by all products xy, where x is in J1 and y is in J2. Essentially, what do you need to do to form an ideal out of a subset, right? You take a subset, to form an ideal out of it, you just need to close that subset under sums and multiplication by ring elements, right? That is essentially what you need to do, right? Now here multiplication by ring elements doesn't matter, right? Because suppose you take r times xy, where r is an element of your ring, then by associativity this is of the form rx times y, right? Now since J1 is an ideal, this is clearly, I mean, this element is clearly in J1 and this element is clearly in J2, right? So we need not bother about multiplication by ring elements, right? What we only need to bother about here is just sums. So you take elements xy, you take elements, let's say st, where s is in J1, t is in J2. There is no guarantee that the sum will also be in this particular set of products only, right? So you need to close it under sums, and that is how you get this one, right? Okay, so this is what precisely happens. So it's the ideal generated by this particular subset of all products x y, where x is in J1 and y is in J2. But yeah, I understand why you wanted to say J1 intersection J2. And so is this true? Is J1 J2 contained in J1 intersection J2? Is this true? What do you think? Is J1 J2 contained in J1 intersection J2? Anyone? Is a product contained in J1 intersection J2?
Yes, sir.
Why?
I have taken any element from J1, J2, which is
Yes.
of the form summation I1 to n xi yi,
Yes.
and this is of the form x1 y1 plus x2 y2 up to so on xn yn,
Yes.
where these xi belongs to J1, ya belongs to J2,
Yes.
and then uh, this whole sum belongs to J1 as well as J2.
Precisely because J1 and J2 are ideals, right? So that
Yes, sir. Yes,
yes,
sir.
they are closed under multiplication by ring elements. So this is certainly true. Now this is something that I leave as an exercise, let's say. So is the converse implication true? That is G1 intersection J2 contained in G1 J2? So I want you to work on this. So certainly this is correct. So this is true. So is the converse also true? J1 intersection J2 contained in J1 union J1 into J2. Is that true? So anyways, we know that C and D are both ideals, and also B. But A is not an ideal unless one of them is contained in the other one. So anyways, let's move on to the next problem. I hope you don't have any questions here. So let's move on to the next problem. So you understand what this is, right? What is this?
This is a polynomial ring with n variables.
Yes, the elements are precisely polynomials in n variables. In other words, it's a free Z algebra generated by this indeterminates x1 up to x. Yeah, so it's a polynomial ring in n variables, right? So which of these following are correct? This is what we have to figure out, right? So what do you think? So what do you think? First of all, is this an integral domain? You know, right? What is an integral domain?
Yes, sir.
Yeah, okay. So why is this an integral domain?
Because Z is an integral domain, and we have result that if R is an integral domain, then Rx is an integral domain.
Very good, but very good. But here we are given, let's say there are more than more than one variables involved, right? But you only said that if R is an integral domain, so R is ID implies Rx is ID, but that's a result only for one variable, right? But we have n variables here. So what is the guarantee that this will also be an integral domain? What do you think? So we know that if R is an ID, Rx is an ID, right? Now can you write Rxy as a polynomial ring in Rx? This is precisely the polynomial ring in Y with coefficients from Rx, right? Isn't it?
Yes, sir. Yes, sir.
So yeah, so R is an ID implies Rx is an ID, and therefore using the same result or applying the same result for the integral domain Rx, we know that since this is an ID, this is also an ID. That is Rxy is an ID, right? And hence we are done. So let me write it in a more convenient way so that we have more space here. I don't know why I didn't leave spaces. Yeah. So option A is certainly correct. Z is an ID implies ZX1 is an ID, which implies that ZX1 X2, which is just ZX1 X2, is an ID. And if you keep on doing this, you get ZX1 up to Xn is an ID, right? This is precisely what our argument is saying. Okay, so option A is certainly correct. There's no doubt about this. What about option B? Is this an Euclidean domain? So you know what an Euclidean domain is, right? It's precisely an integral domain together with a Euclidean valuation, right? So that you are allowed, so that you can actually perform the division algorithm in the ring. So is this an Euclidean domain? Acha, by the way, let me just ask you this. Did you study this, that every Euclidean domain is a principal ideal domain?
Yes, sir.
Okay.
Yes, sir.
Okay. So good. So in that case, if we want, if we want to show that this is not an Euclidean domain, is it not enough to show that it is not a principal ideal domain?
Yes.
Yes. So we can just focus on this third option. So let's see whether this is a principal ideal domain or not. So what do you think? Will this be a PID? That is, whether will every ideal be generated by a single element?
No, sir.
Okay.
Sir.
So can you give me an example?
Sir, ZX is not PID because idle generated by X and 2 is not a
Very good.
principal idle.
Exactly. So you can use the same idea here, right? You can just consider the ideal generated by x1 and 2. That will not be generated by a single element. Or you could just take ideal generated by x1 and x2, let's say. That won't be generated by a single element, right? So zx, so zx1 up to xn is not a PID, as the ideal generated by x1 and 2, let's say, or let's say x1 and x2, for doesn't matter, is not principal. Hence z x1 up to xn is not Euclidean as well. Okay, so this therefore discards options B and C, right? So what about option D? Do you understand what Noetherian rings are, right?
Yes, sir.
Okay. So Noetherianness is one of the most important properties that a ring can have, or later when you study, let's say, modules over a ring, Noetherianness, there is a notion of Noetherianness there as well, and it's one of the most important properties of that an algebraic object can have. So yeah, so what do you think? Will this be Noetherian or not? We won't be giving a concrete proof of this. Instead, we'll be using something here. But I just want to know if you have studied this this week or previously. So what? So have you studied the Hilbert basis theorem?
No, sir, not yet.
Okay. So did they promise they will be proving it sometime? Or is that part of your course or something?
I think Hilbert basis theorem is not in our course.
Okay. Okay. So I don't know why they considered giving this problem, but the point is, so let me just, this is a very powerful theorem in commutative algebra as well as algebraic geometry. So Hilbert's basis theorem which says that if R is a Noetherian ring, then so is Rx, right? So if you take a ring which is Noetherian, then the corresponding polynomial ring over that ring in one variable will also be Noetherian. This is what it says. This is what the Hilbert's basis theorem says. A very simple statement, but with very far-reaching consequences. So from this, can we now deduce that Z x1 up to xn is Noetherian?
Yes, sir.
Why?
Because Z is Noetherian.
Yes, exactly. So Zx will be Noetherian, or rather Zx1 will be Noetherian, right? And hence Zx1 together with x2 will be Noetherian, and so on, right? So now Z is Noetherian implies Z adjoined with x1 is Noetherian, which implies Z adjoined with x1, x2 is Noetherian, and this goes on and on. Xn is Noetherian, right? So that means option A and option D are correct. So I really want you to understand and really understand the statement of the Hilbert's basis theorem. Even though it seems very innocent, but it's very powerful and it has very far-reaching consequences. So it's really, really good. So yeah. And the proof of the Hilbert's basis theorem, by the way, is not very difficult. There is a small trick involved there, but you can always look it up anywhere in. You can just Google it up. It's very popular. You can just write Hilbert's basis theorem and you'll get a proof of this. There is also a very nice story concerning philosophy and mathematics involved here. I mean, there was some argument between two mathematicians and all that. So you can just Google it all and find it. So let's move on to the next problem. Okay, so this is very simple, even though it looks very large or huge, it's very simple. So you understand what the ring of real valued continuous functions on closed 0, 1 is, right? That is, what is C closed 0, 1? You know this, right?
Yes, sir.
So this is, as a set, this is the set of all continuous mappings of closed 0, 1 into R. And what are the operations? The operations are how you precisely define addition and multiplication, right? So f plus g should map x onto the image of x under f plus the image of x under g, and f dot g should map x onto fx times gx, right? And this is also a very general principle in mathematics. So whenever, let's say, you have some kind of object involved, and what you do is, let's say that object is some set, I mean some set with some structure, maybe group structure, ring structure, whatever, and you take a set x and you look at mappings of x into this object, then usually the collection of all those mappings has a similar structure as the codomain object, usually. So this is what also happens here. R is a ring, so C01 is also a ring under these operations, right? So it is certainly a ring, but there are certain problems. So let me ask you this. Do you think that this will be an integral domain?
No, sir.
Why?
So we can consider two functions.
Yes. Yes, good, very good.
Non-zero function whose product is not non-zero.
Yes, so
like we can consider fx as 0 on some point where gx is non-zero.
yes. So I have precisely
Vice
given a
versa.
picture here, right? This is a good example, right? So the blue function, or rather the graph, this is a graph. So the blue one basically represents a function which is, let's say, 0, 1, half comma 1, closed half comma 1, and the other one is 0, 1, let's say 0 comma closed half, right? So the product is certainly 0, but none of the functions are 0. So this is not a ring, let alone an integral domain. This is not, I mean, let alone a field, this is not even an integral domain. So yeah. So certainly we understand that this is a very perfect ring. I mean, it's a very good ring. And now we are taking a subset I of R, which consists of all functions f from close 0 1 into R. That is, we are looking at all mappings of close 0 1 into R such that, so what should a mapping of close 0 1 into R satisfy? This mapping should satisfy that it should map 1 over 3 to 0, and it should map 1 over 2 to 0, right? So you are basically asked to find whether I is an ideal of R. The ring is R. You are just asked to find whether I is an ideal. So what do you think? So will this be an ideal? So just give me 1 second. I'll come. Yeah. So what do you think? Will this be an ideal?
No, sir.
Okay. So why do you say so? So you have a reason, right?
Because I have used basic definition of ideal.
Okay.
Like for I have taken some f from C01
Okay.
and some g from this I
Okay.
and count the value of f of g at 1 by 3.
Okay. No, no, no. There's
But
a
this will not work.
there.
Sorry, sir. This will not
Yeah.
work.
By the way, there's some problem here. We are not saying that. I mean, we are not the multiplication is not composition, right? It's just
Yes, sir. Yes, yes.
yeah, pointwise composition. Indeed, there is no right. I mean, there's no guarantee that you can always compose two elements of C01, right? Two arrows. You have F an arrow and G an arrow. There's no guarantee that the codomain of F will be contained in the domain of G, right? So there's no guarantee that you can compose them always.
Ideal. It's an ideal.
Yeah, it's an ideal, right? Precisely, it is an ideal. And the way to do this is basically you can just use the definition. So take f in I and g in I. This means that both f of 1 over 3, f of 1 over 2 and g of 1 over 3, g of 1 over 2 are 0, right? So this implies that f plus g at 1 over 3 is 0, which is which is f plus g at 1 over 2, right? And similarly, if f is in I and g is in your ring C01, that is R, which is R here, then g times f of 1 over 3 is g of 1 over 3 times f of 1 over 3. But one of them is 0, so the product has to be 0, right? And this is also g times f of 1 over 2. Okay. So certainly it's closed under multiplication by ring elements. So indeed, I is an ideal. Okay. In fact, you can improve here. I mean, you can give a better answer also. You can check. So let's say, so this is a very general thing that I'm saying. I mean, general thing with respect to the specific ring C01. So say you take, so in fact, so the answer will be true, right? So in fact, if A is in C, if A is a point in close 0 1, then you can check this, that this collection MA of all functions, or yeah, I should write continuous here. We are in C01. So let's say all F in C01 such that f of A is 0, that is f vanishes at A. This is an ideal. This is an ideal of C01, right? And what is our given ideal I? I is precisely the intersection of m1 over 3 and m1 over 2, right? Now m1 over 3 and m1 over 2 are ideal, so their intersection will also be an ideal, right? And that's it. Have you studied about maximal ideals?
Yes, sir.
So do you know that this ma that you have considered here is actually a maximal ideal of R?
Yes, sir.
Good. But something more is true here. That is, a converse is also true. So ma is a maximal ideal. So how should I write, or where should I write? Let me just write it here. I is m1 over 3 intersection m1 over 2. Now in fact ma is a maximal ideal of R for all a in C0 in 0 1. But the converse is also true. You can prove that every maximal ideal is of the form ma for some a in close 0 1. This is what you can actually prove. So have you seen this previously, that every maximal
Sir,
ideal?
I have not seen the converse part.
Yeah, so this is true, and here is where you require some topology. Okay, so this is a very nice I mean, it's a very nice junction where sort of to prove something about algebra you are using some result from topology. So precisely what you want here is, what you use here is the compactness of closed 0 1. Have you studied compactness?
Yes, in real analysis.
Okay, so that means at least, not, let's forget topological spaces in general, at least for the space close 0 1, you know that it's compact, and that is every open cover will have a finite subcover, and this is what you will be using to prove this result. So definitely I would suggest you to try this. So what basically happens is that if you take the collection of all maximal ideals of C01, and if you take the set close 01, so you take a mapping, you have a mapping of close 01 into the maximal ideals, right? Every A goes to ma, right? And this what we are basically seeing here is that this particular mapping is actually a bijection. It is, in fact, it is something more than a bijection, but for the time being, it's just keeping things at a set theoretic level. It is a bijection of close 0 1 onto onto the maximal ideals of your ring, right? So in other words, in order to understand the maximal ideals, it is enough to understand close 0 1. You can think of it like this. Anyways, so I hope you don't have any questions here. Let's move on to the next problem. Okay, so this is very easy. What definition of Noetherian rings have you studied?
We have studied that R is Noetherian ring if there exists a increasing sequence of ideals such that their union is some ideal. Means there exists some maximal ideal. Like
I think there is something wrong with the definition, right? I mean, you could say that every collection of non-empty collection of ideals has a maximal ideal, right? I mean, maximal element with respect to inclusion, right? That is one definition.
yes, sir.
Or you could say that if you take any increasing sequence, any increasing sequence of ideals, then that sequence should become stationary at a certain stage, right? Which is by which what I basically mean is that if I1 contained in I2 contained in I3 and so on, in plus 1 and so on, if this is an increasing sequence of ideals, right, then there exists a stage, let's say n naught in natural numbers, such that in naught is the same as in naught plus 1, which is the same as in naught plus 2, and so on, right? After that, everything becomes equal after this n naught stage, right? That is, every ascending chain becomes stationary or stabilizes, or equivalently we can say that there is an infinite strictly ascending chain of ideals, strictly increasing chain of ideals. This is one definition of a Noetherian ring. And again, there is one other way of understanding them or defining them, which is precisely saying that every ideal in the ring should be finitely generated. So have you heard of this?
No, sir.
Okay, so that means we need to prove this. So what we are given here is we are given some which of the we need to find out which of the following conditions are actually true for a commutative Noetherian ring R. So as I already said, option A is correct. So since you haven't seen a proof of this, let's just quickly go through it. Very easy. So we need to show that every ideal of the Noetherian ring R has to be finitely generated. That is, there has to be a finite set of elements in the ideal such that the ideal generated by that finite set is actually the entire ideal. Okay. So let's take an ideal I in R. How do we show that every ideal is finitely generated? I mean, how do you show that I is finitely generated? So let A1 be in I, okay. Consider the ideal generated by A1, this is contained in I, right? Now what happens if this ideal generated by A1 is I? Then certainly I becomes finitely generated, right?
Yes, sir.
So let us assume that A1 is properly contained in I. Okay, so the proof, I mean to be very precise, we'll assume that I in R is not finitely generated. So assume I in R is not finitely generated. So certainly if you take A1 in I, the ideal generated by A1 has to be properly contained in I, right? Because otherwise I would become finitely generated. So that means there exists an A2 in I minus the ideal generated by A1, right? So consider the ideal generated by A1 and A2. This is also properly contained in I, right? This contains ideal generated by A1. In fact, properly contains ideal generated by A1 because A2 has been taken outside the ideal generated by A1. But this is at the same time properly contained in I, right? Because otherwise I would become finitely generated. So that means there exists A3 in I minus the ideal generated by A1 comma A2, right? So again we consider ideal generated by A1, A2, A3. This is also properly contained in I, right? So if you keep on doing this, what you get is that you get an ascending sequence, strictly increasing chain of ideals, right? Sequence of ideals, right? A1, A2, A3. So you get a strictly increasing sequence of ideals. Right? Increasing sequence of ideals. But can such a sequence exist?
No, sir.
Yes, because we started with a Noetherian
No,
ring.
there is.
Yes, this is a contradiction. Hence, certainly we know that I is finitely generated. Every ideal has to be finitely generated. And conversely, this is what I leave for you to try. Even though we do not need the converse one for this problem, but conversely, you can see that if every ideal is finitely generated, then the ring has to be a Noetherian ring. This is one other definition of a Noetherian ring or a Noetherian object, that every sub-object of it has to be finitely generated. Yeah, here we are talking about ideals as sub-objects. So option A is certainly correct. Let's focus on option C first, okay? Then move to the other options. So any quotient of R is Noetherian. You understand quotient rings, right? You have studied ideals. You know that given a ring and an ideal, you can factor the ring out by that ideal, R modulo I. That is a ring, which is our quotient ring. So option C is saying that if R is Noetherian, then any quotient ring of R will also be Noetherian. So what do you think? So let's take R here and let's take I be an ideal in R and consider R mod I, which is our quotient ring. We have a canonical mapping from R to R mod I, right? What is
Yes, sir.
what is that? Every A is mapped onto,
A.
A plus I.
yes, A plus I, the corresponding coset. So this canonical mapping is actually an epimorph. I mean, it's actually a surjective homomorphism of R onto R mod I, right? Okay. Now we want to show that indeed R mod I will be Noetherian. So take, let's say we can use any criteria here. So let's just go with the usual definition. Take an ascending chain. Ideals in R mod I. Okay. So let's say J1 containing J2 containing J3 containing, and so on. So what do you think we should do here? We have to somehow exploit the fact that R is Noetherian, right? We have to use that. And we have obtained a sequence of ideals in R mod I. What can we do? How should we go to R? We have a mapping of R onto R mod I. We have a map from R to R mod I. And we have obtained something in R mod I. How should we get back to R?
To mapping, that's can
Sor-
use
Sorry?
onto mapping, that we can use every element of R by I, that there exists element in R.
That's true. That's true. But we can do something more, something which doesn't even use the subjectivity, right? I mean, you have studied, right? If you take a subset of your codomain, you can always pull it back, right? Take an inverse image. That, I mean, this is what you want to say, but I'm talking about taking inverse images of the subset, right? So basically, we can consider pi inverse of J1, and this will be contained in pi inverse of J2. This will be contained in pi inverse of J3 and so on, right? Now, and we are not using in anywhere the fact that pi is a surjection, okay? This is true in general. The point here is that this is an ascending chain of ideals in R, okay? So you take any ideal in your codomain, if you pull it back, you always get an ideal in the domain, right? So this is an ascending chain of ideals in R, right? And since R is Noetherian, there exists, so which implies that there exists n naught in natural numbers such that pi inverse of j n naught is the same as pi inverse of j n 1, which is same as pi inverse of j n 2, and it goes on, right? Now if these are same, you can apply pi on each of them. So pi of pi inverse of j n naught is the same as pi of pi inverse of j n 1, which is the same as pi of pi inverse of j n 2, right? And it goes on, right? And this is where you are actually using the surjectivity to show that, I mean, to conclude that pi of pi inverse of j n naught is actually j n naught. This is where you are using surjectivity. This is where you need surjectivity, right? So you take a subset, you pull it back, and again you map it via the usual, the given mapping pi, right? So there's, it will be, the image will always be a subset of the original subset, right? But since the mapping is surjective, if you pull it back and then map it again, it will get mapped onto the same thing, right? Precisely onto the same thing, right? Is it okay?
Yes, sir.
Yeah.
Oh.
And this is where you use the surjectivity to, so this holds, which therefore shows that there's what we have here is, yeah, R mod I is Noetherian. So we are using surjectivity, or rather using, I should say. Yeah, so R mod I is Noetherian. And what about option D? We won't be working with this. I mean, we have already mentioned that, so we are given that every sequence I1, I2 of ideals of R will contain a maximal element under inclusion, okay? And this is very simple to see. This is very easy to see. We don't even need to assume that we have a sequence here. Right, we can take any collection of non-empty collection of ideals, there will always be a maximal element. Why? Because assume there is no maximal element, you start with some ideal I1, let's say, then since this is not a maximal element in this collection, there is something strictly greater than I1, right?
Yes, sir.
Maximal means that maximal doesn't mean that that element is maximal if it is greater than equal to every other element. Rather, maximal means that there is no element which is greater than that element. So maximal elements and greatest elements, there is a distinction in the case of partially ordered sets. So maximal, so something is maximal with respect to something means that there is no larger something containing that something, or greater than that, strictly greater than that something and satisfying the same property. So anyways, you take I1, this is not maximal means it is strictly contained in some I2. Again, I2 is not maximal because we have assumed that there are no maximal elements, which means that I2 is strictly contained in I3 and so on, right? So what happens is you get a strictly ascending chain of ideals, right? But that can't happen, right? Because R is Noetherian. Okay. Okay.
Yes, sir.
So D, let's just write easy to see. And what about option B? So every descending chain of ideals I1 containing I2 containing I3 and so on stabilizes or becomes stationary. That is, instead of taking an ascending chain, you now take a descending chain, decreasing chain, and what happens is that any such descending chain of ideals will always become stationary. That is, there will exist a stage after which all the terms of this chain will become equal, will be the same. So what do you think? Does a Noetherian ring have this property? So for Noetherian rings, you know that the dual property in the case of ascending chains holds, right? But does the property for descending chains also hold? So what do you think? I claim that this doesn't hold. I just want a counter example therefore. So you must give me an example of a Noetherian ring which doesn't have this property that every descending chain will stabilize. So can you give me an example in Z? So B is not correct. As a counter example, consider Z is Noetherian, but can you give me an example of a descending chain which doesn't become stationary? So if you just take 2Z, the ideal generated by 2, this properly contains 4Z, right? This properly
Yes, sir.
contains 8Z, which properly contains 16Z and so on, right? Is a strictly descending chain. Right? So certainly option B is wrong. By the way, any ring, we know that any ring which satisfies this ascending chain condition on its ideals is called a Noetherian ring, and the name was given after the famous lady mathematician Emmy Noether, right? So rings which satisfy the dual property, that is every descending chain of ideals stabilizes, such rings are called Artinian rings. And they were named after Emil Artin. So you guys have seen that book by Michael Artin, right? That Algebra, maybe just Algebra. Artin's book.
Yes, sir.
Yeah. So this Artin is actually the son of Emil Artin. Yeah. So we just are left with the final problem, which is problem 7, and after that we can end the session. So let's just quickly go through it. So which of the following is the correct sequence of implications? We have a sequence of implications. We just need to find out which of them are correct. So this is part A. So is A correct? That is it true that if we have a PID, then it has to be an ED and therefore an ID? In particular, is every PID an ED?
No, sir.
Okay, so can you give me an example?
Z of 1 plus minus under root minus 19 over 2.
Yes.
This is a standard example.
Yes, very good. So 1 plus root minus 19 over 2. Yeah, why did I write as? Sorry. A is not correct, as Z of 1 plus root minus 19 over 2. The subring of C generated by Z and this thing is a PID but not a ED. Okay. And it certainly has a proof. The proof is a bit it's a bit algebraic number theoretic, but yeah, it's very accessible as well. You can just Google it and you can find number of PDFs. So is option B correct? Every ID is a Euclidean domain, which is therefore a PID. Is option B correct? Is every integral domain an Euclidean domain? So B is not correct, right? As Zx itself is an Euclidean, is an integral domain, but not a principal ideal domain, right? Isn't it? You only said, na?
Yes, sir.
Yeah. So Zx is an integral domain but not a principal ideal domain, and hence it can't be an Euclidean domain as well. So is option C correct? Every Euclidean domain is a principal ideal domain, which is therefore an integral domain. Is this correct? You have studied, right, that every Euclidean domain is a principal
Is a
ideal?
PID.
Yes.
Sir.
Yes. So you have seen the proof as well, right?
Yes, sir.
Yeah, it's very simple. What you do is you take this any ideal, you need to show that it's principal. That is, you need to find a single generator of that. So what you do is you consider an ideal and you look at the valuations of all the elements there, and you just look at the smallest positive valuation, element with the smallest positive valuation, some element. You just prove that that will generate the ideal. That is what the idea is. And that is where you need to use the fact that you can perform division algorithms in an Euclidean domain. So option C is true. Very standard. So and certainly every PID is an ID, right? Principal ideal domain is an integral domain by definition. And is option D correct? Every Euclidean domain is an integral domain, and every integral domain is a principal ideal domain. Is this
No, sir.
no, right? And we saw Zx. So this is wrong. So this is wrong, as Zx is an ID as we just wrote here, but not a PID. Yeah, we can also write, we can write ED here. Yeah, well, I mean, doesn't matter really, but yeah. So that's all from my side for today. So do you have any questions? And if not, we can just end the session.
No, sir. Thank you so much.
Okay. Thank you for joining. We just stop the recording.